exploring various cell and module technologies such as TBC, perovskite lamination. Tongwei Solar has independently developed the TNC high-efficiency cells, the mass production conversion efficiency of which has reached over 25.4%. Among the leading manufacturers that have taken the lead in entering the HJT field, Tongwei Solar's HJT cells have achieved a maximum R&D efficiency of 26.07%. Tongwei Solar continues to update its technology pool with emerging ones and always stays at the forefront of the industry. Ranking on the Tier 1 list, it has currently obtained national and regional certifications in major markets such as Australia, Japan, and France. Tongwei Solar's high-efficiency modules are suited for household rooftops, industrial and commercial distributions, large ground power plants, etc., boasting a perfect and professional service system and a high standard of supply quality. Tongwei Solar can meet global customer needs in all respects. Tongwei Solar's high-efficiency modules have cooperated with multiple projects around the world. Its products are exported to more than 40 countries and regions such as France, Germany, the Netherlands, Chile, and so on. Carbon peaking and carbon neutrality goals have become a global consensus. PV brings together the momentum for green development to create a better future and achieve the sustainable development of humanity. Tongwei Solar. PV changes the world.
What is zero? It can be zero distance, bringing solar energy to every corner. It can be zero error, representing our attitude to the products. It can be zero destination, representing our pursuit of advanced HJT technology. It can be zero carbon, contributing to build a cleaner world. So what exactly is zero? Zero is the goal, a goal that drives us forward, fuels our passion, and defines our purpose to shape a net zero future. Zero is everything.
Since 2008, Glasmanufaktur Brandenburg GmbH, as part of the Interfloat Group, has been producing high-quality glass for photovoltaic and solar systems, as well as for greenhouses at their Tschernitz site in the south of Brandenburg, a historical glass-making region. 365 days a year, high-quality glass paints are produced from sand, dolomite, soda, cullets and other raw materials. More than 300 employees, as well as up to 60 temporary agency workers, work for GmbH, making it one of the region's most important employers. To produce high-quality, low-iron glass, it is necessary to use premium raw materials. Being a supplier for GmbH requires auditing according to ISO 9001. In the batch house, the raw materials are weighed and mixed following the company's own recipe. Batch feeders then carry the finished batch in the melting tank. In the melting tank, the batch is melted to a liquid mass at up to 1600 degrees Celsius. To this end, the GmbH melting tank is fired using natural gas and oxygen. This is currently the most environmentally friendly firing method for melting tanks and sets us apart from our competitors. Highly qualified employees monitor the production processes in the control room. The liquid glass is fed continuously to the two production lines where, at a temperature of around 1000 degrees Celsius, it is discharged onto the rolls with a width of 2.4 meters and a height of approximately 7 centimeters. Standard glass thicknesses are 2, 3.2, 4, 5 and 6 millimeters. Different glass patterns enable different applications. The pattern of the glass minimizes reflection, meaning the sunlight is guided into the glass and thus onto the PV or solar module. After rolling, the temperature of the glass is reduced to around 80 degrees Celsius by transporting it on water-cooled transport rolls and ceramic rolls so as to ensure break-free cutting. The edge cutters score the side edge strips and then break them off. The cross cutter splits the glass ribbon into stock plates. The first inspection takes place during this step of the process. The position and size of defects, such as bubbles or seeds, is registered and evaluated. Two fully automatic and computer-aided cutting lines make optimum use of the glass ribbon for each blank. This enables even small production series to be produced according to customer wishes. For finishing lines are able to flexibly accommodate the individual wishes of
Hello everyone. My name is Wenjing Wang. I'm the chair of this section. So let's start this section, the topic. The first will be Mariana Botany. She is a professor of Arizona State University. Welcome.
All right. Well, thank you to the organizers for the invitation. Thank you for the introduction. I'm going to try to maintain my 15 minutes, just like all the other women in the first session, and keep the record. So what I want to share with you today is some of the work that we've been doing at Arizona State University, working on some degradation of heterojunctions from the very fundamental side. So we're going to go from atoms to the field. So let's get started. All right, so quick outline. We'll talk briefly about some observations. We'll talk about test structures and the degradation of test structures. And then we're going to talk about the degradations of some silicon heterojunctions that we put in the field. And hopefully I'll summarize within 12 minutes. And hopefully this works. All right, so many of you are familiar with some of these reports of degradation of some silicon heterojunctions that have been fielded at NREL, so that's in Colorado. And this is courtesy of Dirk Jordan. What you see in here is basically two sets of different modules. One is the Sanyo module that was fielded in 2006, and then you have some Panasonic modules fielded in 2018. So in general, the observation, and many of you are very familiar with this, is you see a big degradation or a substantial degradation on your VOC. In some, you also see an increase in VOC at the very beginning. So what I want to talk about today is what is happening fundamentally at those interfaces and what mechanism governs this behavior. The other thing that you are also very familiar with is some efficiency gains that you actually see when you light soak your modules. I think we've seen some of the talks early this morning talking about this behavior. And I think all can be explained by describing a little bit of the interface. So let's get started. So what is our approach? So the way that we actually tackled this problem was to have a top-down approach and a bottom-down approach. So we built it different layers. So we built the heterojunctions up. So we started with a good quality silicon. we put amorphous silicon, intrinsic amorphous silicon, dope amorphous silicon, we did symmetric structures, and then we did SIMS, ECV, we threw the kitchen sink at these interfaces. The other thing that we also did is using the same or very similar silicon quality, we fielded several amount of modules, and we also look at some modules that have been in the field for quite some time. And hopefully, we put some modeling people to work, some molecular dynamics, some ab initio calculations, and we could bridge the top-down approach and the bottom-up approach. So there's going to be a whole lot of atoms in the next couple of slides. So the first thing that I want to chat about is to J0 or not to J0. So many of you, when you talk about surfaces, you love to talk about J0s. And I beg you to stop talking about J0, because as our cells start getting better and better and our maximum power points start shifting towards higher and higher injections, your J0 does not necessarily describe your surface recombination velocity. So that was my little caveat here, and then we can move on. All right, so how do we look at surface recombination velocity? How do we do this analysis in a way that is experimental, right? And the answer is you actually have to create a whole lot of samples. So you create a thickness set with the same wafer quality and basically different thicknesses. You have to coat your system symmetrically. So if you want to look at intrinsic amorphous silicon, you do intrinsic amorphous silicon both sides. You want to do a dope layer, you do a dope layer, the same dope layer on both sides. And then what you can actually do, because you know that 1 over tau efficient is effective is 1 over tau bulk plus your surface recombination velocity parameters, then you can actually extract your SRV out of your linear response. So that's a little bit of what we did in this work. And so there's a lot of samples in here. You're going to see a couple of points here and there, but these are like many, many, many samples. Once you get your surface recombination velocity, you can use the amphoteric defect model, which basically has 3 different states for hydrogen, and you can actually fit your interface defect density and your charge density at the interface. If you fancy looking at the bulk, you can also take a look at the bulk, but that's beyond what we're going to be chatting about today. I'm happy to chat with any of you that are interested in it. So let's take a look at some data. So one of the things that I forgot to mention in the previous slide is that we did surface recombination velocity, and then we have a bunch of samples that were under light and under heat. Some were light and room temperature, some were curved in the dark. And so a little bit of what you see in here is basically a year and 2 years of tracking this surface recombination velocity as a function of time under different conditions. So let's just pay attention to the blue and the black, which are basically 1 sun at room temperature and 1 sun at 8 degrees Celsius. Let's forget about the dark, because the dark is not the dark, but you get this particular response that follows a stretch exponential behavior, which has the signature of a distribution of states, right? A distribution of transformations. And you can very well fit this curve, which is the interface defect density, with a stretch exponential behavior like this. And one of the things that you would notice if you take a look at this, you do this, is that your defect density at the interface changes and increases as a function of time, but your charge density at the interface stays put for the intrinsic amorphous layer. The dope amorphous layer has a change in QS, but I have a limited time. I'm happy to chat about the dope layers later. So the other caveat here, if you shine light, it's not a dark measurement. So that just sounds quite obvious, but when you keep things in the dark and then you go and do like a symptom test, you're actually shining light. And so a lot of the degradation that you actually see in here really is a consequence of the flash. So just caveat, and for those of you who are a student here, just be careful. It's like kind of the Schrodinger cat, right? It's dead or alive, and you're kind of killing it. So, and what you see on the right-hand side is basically some molecular dynamics calculations that basically shown that really in the dark, you shouldn't have a whole lot of problems and a whole lot of changes, just basically a pretty stable interface, as long as it's an amorphous silicon interface. So when you actually start looking at the stretch exponential behavior, so here we have like the light degradation and the room temperature, and then you have an extra bump when you apply light. You basically start seeing, and this is me trying to express the, all the molecular dynamics in like sticks and balls. You basically have a dangling bond that gets, that basically retraps your hydrogen, and then your dangling bond moves back, and then you create another dangling bond. So you basically, like, your interface becomes extremely sensitive to light. And many of you have seen several papers from, a couple of decades ago proposing similar behaviors. So a quick comment here on the change that we observe of defect bond density at the interface with illumination time. This is nothing really new. This was proposed by Strootmans back in the 80s. But your NA, the saturation level for your defect density at the interface is basically the rate of creation of new dangling bonds, which decreases with density of already existing dangling bonds. So basically, the more you have, the less you create, which kind of makes sense. And then you have your tau zero and your beta factor in your equation here, which describes basically the relaxation towards equilibrium. And that basically depends on the efficiency of the creation of dangling bonds and the different transformations that you have. And I'll mention some of the transformations in a second. And I think the bottom line really is that, and part of like what Strootmans actually proposing back then was that the defect generation really is proportional to your MP factor. So here's where we started like doing a little bit more digging and trying to see what was going on really at the interface. And so what we did was we took this fit from this equation, and then we transform it into VOC, and we actually fitted perfectly well the Sanyo, the very old Sanyo modules degradation, when we actually take a look a little closer and we measure the IVOC by using some CRE. We actually also see that the drop matches actually quite well with the same behavior that we observe in the modules. So we take a look at the stacks, and the first thing that we observe is that we have a fair amount of hydrogen that is actually leaving the interface. So these are glow discharge optical emission spectroscopy measurements. The as deposited is the green. The 7-month exposed is the gray, and you can of course do this measurement after several months and even a year, and the drop is very sharp at the very beginning, but then it plateaus. You may be asking what's going on here. Why is there a shift? I think that has to do with the homogeneity of our deposition, since these are not exactly the same samples. So the main observation here is that we actually see about 18% loss of hydrogen at the crystalline silicon amorphous silicon interface. So the next thing that we did was to ask our modeling collaborators to take a look at, what are the transformations, what is actually happening at this particular interface. And so the first thing is that there's several amount of reactions taking place. So here's your crystalline silicon, here's your interface, here is your amorphous silicon. And from all of these reactions, several of them have a pretty low formation energy. The first one really is a hydrogen bonded to a silicon 3 in an amorphous state that would always tend to crystallize. And this makes sense, right? Like, you are very familiar with trying to apply some heat into amorphous silicon and how it tends to crystallize, right? So the next thing that we asked them was, okay, what happens if you shine light? So when you shine light, the formation energy of this reaction that we call number 8 for some bizarre reason, and number 3, which is basically the formation of 2 double bonds the formation of two dangling bonds, and then the regeneration of one of the dangling bonds actually drops dramatically. And so a lot of the formation of the dangling bonds at the interface really comes from actually the formation energy of this transformation. All of these reactions really actually make also a very good point that it does represent what your stretch exponential is actually modeling. One quick thing that I want to note is that we have done a whole lot of modeling. So 1 to 8 are like all these transformations that I mentioned before. We've done the same calculations for different temperatures and different doping. And all I want to say here, because I don't have a lot of time, is that doping plays a very important role in promoting the hydrogen mobility. So you can see how the energy dramatically change if you have, amorphous silicon oxide, or if you have just a pure amorphous silicon N or P type. And the other thing that I do want to mention is how important is the control of morphology and coordination neighboring atoms in your amorphous silicon. So the next thing I want to briefly chat about is what happens when we go from modules to test structures. So same thing. Now what we did is we core out a bunch of structures from the modules, and we measure basically the IVOC. And one of the things that we see right away is that this is the initial value, and this is the module after a whole lot of months in the field. The first thing that we see is that our IVOC and our VOC is actually pretty similar, which suggests that the majority of our recombinations are coming from non-radiative recombination. The other thing that we also see is that when we do a glow discharge optical emission spectroscopy for modules that have been fielded in Florida or in Colorado, we see a gigantic drop in hydrogen in the TCO, which is something kind of strange. And then also the amorphous silicon interface that we saw in the stacks. Finally, the other thing that we see is a change in the oxygen concentration. So let me just move, because I don't have a whole lot of time. I think the important thing to note in here is that, did I press too much? Okay, so you have a hydrogen concentration variation. This is the control, the module that was kept outside. Then you have some weather in a humid environment, some weather in Colorado. You see a significant drop in hydrogen in the TCO and a drop in the amorphous silicon. So surprisingly, we actually see a very different drop in the concentration of hydrogen in the TCO. And the other thing that we observe is an oxidation of the modules that were fielded in Colorado more than the ones that were in Florida, which is actually quite interesting because you would think Florida is humid, you have a bunch of water, then you oxidize everything. But the truth is that when you start looking at some molecular dynamics, you see that the number of oxygen bonded to silicon in the dry exposure is much higher than what you get in the wet. I'm almost done. So the moral of the story is that heat and illumination promote the hydrogen diffusion towards the interface and into the TCO. In dry conditions, the loss of hydrogen is compensated by the oxygen actually entering the TCO, which enhances the silicon oxidation. So you end up having a thicker silicon. It's a thicker oxide, basically, at that interface. And I think hopefully Dana will show you some of those great results tomorrow. And in wet conditions, the TCO has a higher content of hydrogen, which limits basically the out diffusion of the hydrogen itself. All right. And one final thing is that many of you have probably seen some weird things happening in the TCO. Yes, weird things happen in the TCO. When you start actually shining UV light in the TCO on top of your amorphous silicon stack and you see that hydrogen basically out diffusing, you start seeing a lot of changes in your carrier density and a lot of changes in your mobility. And that usually originates from creating some deep electron traps and some shallow states. And I'm happy to chat about those if you are interested. I'm going to move on to my acknowledgments to the people that do the work and take any questions. Thank you.
Time limit, so it's, we will transfer to the next speaker. The next is Paul Prosel Moya. Is a researcher from the Dorfter University of Technology. Thank you.
Thank you. Thank you, Chairman, for the kind introduction. Thank you, everybody, for coming to my presentation. So let me start with the motivation of this study. So first of all, we want to recognize the very nice achievements developed by TRISON and CNH collaborations who are working together in the development of two-terminal perovskite and silicon solar cells. Aiming at the commercialization, they already achieved, as announced previously, 29.8% in a wide area, 9 centimeters square. The need of having an advanced opto-thermo-electrical modeling is crucial for optimization and performance evaluation of the solar cell, but it's more interesting when we are able to assess the consequences of the cell level designs and choices in module level and system. With this, there's available already the challenge to set up a holistic simulation framework to integrate all the different spatial scopes from interface to cell, to module, and to system. So with this, let me introduce the foundation of our work, which is the PBND toolbox. It consists in a cell-to-system holistic model. So we start first, let me introduce the solar cell that we're using for our study. It's a bifacial solar cell developed by TRISON. So with this information, we set the optical system, and we model via ray trace and with our in-house simulation platform, GenPro4. And from that, we can have some outputs. So note here the colors that we are using in this slide. So we have this light blue it refers always to input. Static, we will use static is time independent, where output means that we have directly the output of different blocks. That in fading means that it will come as input for another module. So from the ray trace way optics, we get the generation profile. We get the absorption as a function of the incident angle and wavelength. So from the approach to the module level, so we can, with this environment, we introduce the module. We have an input, the module dimensions and surroundings, and we call the system the module stage as lux, and we get again the absorption as a function of the incidence angle and the wavelength, but it's a module level. With this information, we can now bring that into the transposition models, in which we use also an input properties as time related, with irradiance and smarts. So here we can relate to locations, and we introduce information about location and also about weather. So with this, we can get an absorbed irradiance of the module. And going further, we have the fourth stage, in which we use the absorbed irradiance from the previous module, and we can, together with the ambient temperature, wind speed, and conventional emissivity of the system, of the environment, we can get the cell temperature, and this is the input. And here I would like to come back to the previous and initial stage where we analyze the optical system. From that, we get the generation profile, and from the generation profile, we introduce the basic semiconductor in a module in which we include the semiconductor equations. We evaluate the physics of the interaction between layers, heterointerfaces. We base our study in Synopsys and ASA, which is in-house under development software. And from this, we can reach the compact model, the one or two diodes model, depends on the device. And with this information together, we can anticipate that we can merge everything in one module, in one system. And we can include we can include information from the solar cell. We add interconnection properties of the module with the information of the irradiance in terms of implied photocurrent and with the cell temperature. With this information on the module, we get the power output of the module as a function of irradiance, temperature, and time. Further, ultimately, we can use a model which includes variables as parameters related to the inverter types, and we can get the conversion DC to AC energy yield and the power series. So saying this, I would like to stress that how is relevant this, because from the cell level, we can get information to module level. And with this, I would like to say you how we are organizing our results. So first, we want to talk, we make an evaluation of the cell level, in which we include the validation or modeling approach, first for single junction and then for tandem system, tandem device. Further, we make the optimization of the silicon interaction solar cell. We will present a comparison of the current densities for different tandem devices too, different architectures. Then we can, with this information, we calculate the module level performance. So we build up the module archetypes based on single junction and dual junction devices. We perform simulation in standard test conditions, and lastly, we will present the results at system level in different locations. Let's start with the cell level results. So here we have our baseline device. We are using as reference our model baseline. So we are using relative comparison. So it's interesting to say that the variation in the different external parameters is minimal. So we can say that this is the simulation model. It can replicate the inner physics of the solar cell baseline. Further, we perform optimization given some assumptions from the production line where the solar cell is fabricated, with some working out with the HDL properties, density of states, bulk resistivity, and different TCO options. We were able to model and predict an optimized device with the parameters that we can see, almost one more point absolute efficiency value. And moreover, for the comparison purpose, we will see later, we make the approach of this bifacial solar cell and into monofacial solar cell. Monofacial is here, in which we introduce an EVA and a backsheet as a back reflectors. This will be used as reference to later on, and here we can see how the efficiency is expected to improve. The validation of the tandem system, or the tandem solar cell. So here we have now the tandem device we use again as a baseline. This collaboration with our colleagues from Trisound and CANES. So again, we present the model measurement compared to the comparison between modeled and measured. So we can see that the parameters are in a reasonable agreement with the tandem device, and furthermore, we simulate the EQE that replicates almost perfectly the bottom cell response, the spectral response, and the bottom cell, and of course the total system is already there. So we can be very confident that the physics inside our model platform replicates the tandem system that was proposed. This tandem system was developed considering the flat interfaces and from the bifacial. So it's flat in the rear side, flat in the front part of the bottom cell, and flat in the front part of the top cell. So we call this flat and flat, because we can also simulate different tandem systems based on this on these interface shapes. The first one we call the flattened texture. So it should be the body interface of the top cell should be flat, and the rear side of the bottom cell should be texture. So we also have the texture option, and finally we have this replete structure in which we have some groups that they're very interested in. For this evaluation, we make the assumption that all the layers and the bulk properties of all the layers remain the same. So that's one of the assumptions we do in this study. And here are the main results in terms of short-circuit current, which is the more interesting parameter to analyze within these devices. So we take as reference the flat system, and here are the differences respectively. So the most promising in terms of current and light trapping is the texture system. Here is the efficiency as compared. Here is as compared as the monofacialized system. So here we took as reference, and we can see compare this solar cell to the tandem system, so we can see that the efficiency is remarkably higher. With these results, we can use this into the module level. For the module level, we use different archetypes. So from single junction and dual junction devices. So each module has their own properties. In this case, we assume an M2 that will be used as reference for homojunction and dual junction. So it consists of different archetypes depending on the wafers, how had been cut, the number of strings, bypass diodes, and the area of the module. So we can expect that the higher the area, the higher the output if we have the same system, but we will see later how the results are coming out. Here are the first results from the module level. So here I'm showing the power output as a function of the module type. So for different modules, different solar cell structures. So here in the black box, you can see that's all the results are related to the M2 configuration module. And here I use a dashed line to separate the single junction in your left-hand side and dual junction in the right-hand side for the different interfaces in the tandem system. Here, and additionally, we consider G12.1, G12.2, and G12.3 just as comparison. Of course, the area is bigger, so it's also in favor of these bigger modules. So there are main results, and there's a remarkable improvement in power output of the modules as compared to the monofacial module. So we compare this, it's a very high improvement. Now let's go to the system level. Let's have the results. For that, we choose two different locations in North Europe and Southern Europe. We use the azimuth, a constant azimuth as south because both were in the North Hemisphere. Tilt, we use a constant value of 25%. This is not the best one, but we use a standard for this study, for this comparison. The module height is 1.5 meters. The albedo, we use albedo 0.2, and we use we made the assumption that the albedo has the same spectral richness as AM 1.5 spectrum. And the horizon is free, so there's no obstructions in the horizon in the sky view dome. And here are the results again. But here, note that we have the improvement in energy yield in percentage with reference the monofacial module. Here I use the same note here that the difference in the colors in the border and the boxes it means for the north blue and orange for the south location. Here we have the different modules types, and again. We have for M2 and for G12. The energy yield is consistent with the results of the power output, so we have a massive improvement even to 31%, depending on for the south location, and in the northern location of Europe, 29.19. With this, I arrived to the conclusions of this study. So we are able to go from accurate simulation to energy yield prediction. We evaluate cell-level devices, silicon heterogeneity optimized. With this information, we go further for monofacialists and two-terminal tandems. We evaluate module levels with the different archetypes. We found that the power output was a massive improvement, capable to achieve even to around over 27%. And from system level, we already observed results for module types. For G12.1 should be the most promising. The texture configuration for module and system level, it delivers the highest energy yield. For the northern part, about 29%, and for the southern part, the 31%. As outlook, we want to include for this study a spectral analysis. We're going to include also more locations if possible. We want to make a deep analysis on the temperature coefficient, the urban, include urban environments with the urban horizon, and I include the AC side energy yield for further results. With this, I would like to thank to you for your attention, the funding, and my colleagues for the support of this work.
Yeah, okay.
What about luminescence coupling? Can you account for luminescence coupling between the top cell and bottom cell?
Yeah, so you mean the light coupling in between?
No, the emission of the light from the perovskite cell absorbed.
So you mean the light emitted by perovskite? Yeah, it's not included so far, but we are developing some advanced simulations in which we include this. I think it's a kind of photon recycling. It should be a phenomenon because we can, the combination in perovskite is produce light, so we can recycle these photons indeed. But I cannot say that should be accurate, but maybe it should be a small improvements. It should be 1 + 1 photon recombining can produce 1 electron, so the difference should be small, but of course, interesting to study.
So, the other question?
It's just a question. Is it your module and system level available as open source, or is something?
Actually, it's not an open source. The simulation model is from the PVND toolbox from module level to system is not now it's still under development. This still is we are restricted to use to that for now. So this about the intellectual property, I think it should be another level to talk about.
But are you thinking to provide this as an open source?
Yeah, actually, the software can be available. Eventually, if we have a exchange email to have some agreements, we collaborations for having that incoming results of the application.
Okay, because it's a time limited, so okay.
Can you in the system level simulation, what type of solar spectra did you use? They are different from north and south, or is AM 1.5G?
It's different. It's different. It depends on the location, depends on the temperature, the average temperature. So it's a database that is used from SMARS.
So, but that's an average over 1 year with the change?
Yes. I'm not a specialist on that part. I need to confirm, but is related to a database. So it should be around 1 year, around 2 years, yes. So it should be, that part should be depending on the input that we give to the software. But we use a database for this, feeding this part. I'm not so, for now I cannot say this how many years before you had the database. And
So we have to transfer to the next speaker. So thank you, Mr. Paul. The next speaker will be Yifeng Zhao. He's a postdoctor come from the Delft University of Technology. Please.
Thank you, Dr. Wang, for your kind introduction. Good afternoon, everyone. So let's start. So as most of you already know, that front-back contacted silicon heterojunction solar cells have achieved a remarkable efficiency of 26.81% and a GSA of 41.45 milliampere per square centimeter. And this design features simple fabrication process, but however, the GSA is limited by the optical losses such as front grip metal shadings and also parasitic absorption losses due to the full area TCO and thin film silicon layers. So alternatively, interdigitated back-contacted silicon heterojunction solar cells can offer optimum front light management. And with this, record efficiency of 27.3% and also a GSC over 42 milliampere per square centimeter have been demonstrated. But a typical IBC fabrication process is rather complex. So in the view of a straightforward fabrication, like front-back contacted silicon heterojunction solar cells, can we stick to this design but keep minimizing the optical losses of this design? So to answer this question, so let's firstly look at what are the main aspects that we can improve the light management of this design. So start with reducing the metal shading losses. So metal electrodes should, with high aspect ratio and optimum pitch, should be designed. And with this, various metallization techniques have been developed. And further, to reduce the parasitic absorption losses in the TCO layers, so high mobility TCOs that can simultaneously enable high transparency and high conductivity are preferred. And further, for silicon thin film layers, including doped layers and also intrinsic layers, should be transparent and while being efficient for carrier transport. And one common approach is to alloy silicon thin film with either oxygen or carbon, along with developing nanocrystalline silicon materials. And alternatively, one can also replace those silicon films with transition metal oxide layers, and which are typically more transparent and while being efficient enough for selective transport of charge carriers. And last but not least, you can also enhance the infrared response of the heterojunction solar cells by adding a rear reflector. So overall, to improve the light management of the front-back contacted silicon heterojunction solar cells, especially minimizing the parasitic absorption losses induced in the TCO layer and also silicon thin film layers, often involves trade-off between the optical and electrical properties of the layer. So what if, instead of considering all these trade-offs, can we just simply localize those TCO layers and the silicon thin film underneath the metal contacts? And then we can deposit anti-reflecting coating layers on top, and we form the so-called front-back contacted silicon heterojunction solar cells with localized contacts. And in this design, the collection of electrons rely on their lateral transport in the crystalline silicon bulk. So to understand the potential of localized contacts heterojunction solar cells, so we perform TCAT Centaurus simulations. So here we varied the pitch of the design and also the thickness of the wafer. So here I will present the simulation results of the solar cell performance. So first, as for the JSC gets higher when you use the thicker wafer and also a larger pitch, which is expected. And as for the VOC gets higher when you use thinner wafers while being not very sensitive to the pitch size variations. And the higher VOC, the higher VOC is ascribed to the reduced volumetric recombination due to the thinner wafer used. And then we look at fill factor. So the fill factor gets higher when you use thinner wafer and also when you use a smaller pitch. And in fact, the fill factor trend reflects that the vertical transport of electrons is affected by the wafer thickness, while the lateral transport of the electrons is affected by the pitch. And in this case, both effects have comparable level of influence on the cell fill factor. And eventually, for the maximum efficiency, there is a careful trade-off of the GSC and fill factor, and the optimum pitch we calculated is 800 micrometer, and the thickness of 60 micrometer. by further optimizing the wafer resistivity to 10 ohm centimeter, we can achieve a calculated efficiency of 28% and with a JSA of 42 milliampere per square centimeter. And this is close to what IBC cells can achieve. So experimentally, some intermediate structures of this type of solar cells have been demonstrated. So in an attempt to fabricate TCO-free heterojunction solar cells, people have tried to remove the front TCO or either localize the front TCO layer. And in both cases, the electrons are forced to laterally transport in the crystalline silicon wafer. And later on, there is a more recent study that reported the localization of both TCO and doped layers. And among those studies, the localization patterning were realized by deposition through hard mask, and which often requires careful optimization of deposition conditions through the mask, and also requires careful alignment of those hard masks. And furthermore, those metallization techniques realized either by sputtering through hard mask or screen printing often features a pitch size around 1.8 millimeter to around 2.0 millimeter. And according to our simulation before, the optimum pitch is 0.8 millimeter. So to address its issue, so here we introduce a self-aligned front-back contacted silicon junction solar cells with localized front contacts, a process to develop that. So first, let's start with the baseline heterojunction solar cells we have in our group, so which is around 24% efficient, that features nanocrystalline silicon-based P-type layer on the rear side, and a bilayer N-layer stack consists of N-amorph silicon and N-type nanocrystalline silicon layer on top, and finished with copper-plated electrodes. So let's have a closer look at our copper-plated electrodes, which has high aspect ratio and also conformally plated on the surface. And if we look at the solar cell that we made, and thanks to the plated narrow copper electrodes of around only 15 micrometer wide, and we have a metal coverage of 1.5%, and also a pitch size that is around 900 micrometer, and this is close to our optimum pitch value according to the simulation. So in our group, we developed a self-aligned fabrication process that's utilize the metal contact as the etching mask to fabricate this process. So here, we pattern the TCO using hydrochloride etching, and then we etch the doped layers, namely the amorph silicon and nanocrystalline silicon, by using potassium hydroxide etching. However, there is almost no etching selectivity between the N-type layer and the intrinsic layers. So therefore, the intrinsic layer will be also removed away, and repassivation is needed. But if we look at the device, we have copper electrodes that is already there, so it's not easy to repassivate due to the copper electrodes. So it is, of course, desirable to keep the intrinsic amorph silicon layer untouched. So for this purpose, we introduced additional stopping layer, that is N-type nanocrystalline silicon oxide layer, and which was proven to be etching resistant and also efficient to be act as a part of the electron transport layer. So with this layer, we can etch TCO, we can etch the N-type amorph silicon and nanocrystalline silicon layer, and we stop here, and we deposit further on silicon nitride and MGF2 layers for the light management. So for this type of design, it is very important to understand what's the effect of the TCO patterning on the series resistance of the solar cells. So here, that's why we tried various N-type layer combinations, and the first one is a fixed 4 nanometer N-type nanocrystalline silicon oxide and the various thickness of the N-type amorph silicon layer. So as you can see, despite the very low series resistance below 1 ohm square centimeter before the patterning of the TCO, all of those cells have significantly increased series resistance. So next, by replacing the amorph silicon with the N-type nanocrystalline silicon layer, as you can see, with the thicker nanocrystalline silicon layer, you can minimize this change and even reduce the series resistance after the TCO patterning. However, if the nanocrystalline silicon layer that is too thick, that can also increase a bit challenging for later on patterning this silicon layer. And further on, we combined our optimized bilayer stack and with a very thickness of N-type nanocrystalline silicon oxide. And as you can see, with the thickness of 8 nanometer, And basically, we can control the device series resistance consistently below 1 ohm square centimeter, even after patterning the TCO. So it is known that nanocrystalline silicon-based materials have thickness-dependent conductivity or activation energy. And those observations or those results tells us that a low activation energy of N-layer stack can minimize the contact resistivity, and which might have a hint on the critical rules for less resistive natural transport of electrons in a crystalline silicon wafer. So next, let's move to the optical performance analysis. So let's start with a traditional full area TCO and the full area doped layer solar cells with additional anti-reflection layer MGF2. So we look at optical performance only at the under unshaded areas. So here we show the mirrored EQE and the reflectance as reflected in as shown in the white dot and also the dashed line in the plot. And then to understand the optical loss of this device, we also performed the optical simulation. And as you can see, with this conventional heterojunction cell design, we have a JSA EQE of 39.56 milliampere per square centimeter. And further, based on the mirror EQE and the reflectance, we also plotted the parasitic absorption losses, and which is highlighted by the shaded area. So then we localized the ITO. And as you can see, the JSC is improved further to 40.2 milliampere per square centimeter, and the parasitic absorption loss is reduced. Further, by localizing ITO and doped layers, and we can achieve a JSC EQE almost 41 milliampere per square centimeter, and a parasitic absorption loss reduced of 1.22 milliampere per square centimeter. So with the proven optical enhancement of this design, so now let's look at the Jerry parameters. So we start with a conventional heterojunction solar cell, full area TCO, full area silicon layers, and the Jerry parameters and the Jerry curve is given here. And with the same cell, so we process this initial cell by a localization process we introduced before, and by adding extra double layer anti-coating, and we can see that there is a significant boost of the JSC, and also, most importantly, without compromising any VOC and fill factor. But to have a fair comparison, we also introduced this additional cell that has the conventional design, but also with this dual layer anti-flame coating, so to have a more comparable JSC or reflection loss. So with this, we can further see that the JSC is indeed solidly improved with 1 milliampere per square centimeter, and without losing any fill factor or VOC. And it is very worth to mention that we still have a significant room for further the JSC enhancement. For instance, by fully localized front layers, including intrinsic layers, and also these N-type nanosilicon oxide layers. And also, we can improve on the rear side by using high mobility TCO and also the rear reflector, as we introduced before. So in conclusion, so we successfully developed a self-aligned process of localization of the front contact stacks. And also we found potential critical rules of the low activation energy and the contact resistivity of the N-layer stack for less resistive natural transport. And lastly, we also demonstrated a solid JSA gain without compromising any fill factor or VOC performance of the solar cells. And with this, I would like to thank you for your attention.
There's a question. No question? Okay, it's very clear, so
Okay,
thank you.
Thank you.
So the next speaker is Mahmoud Anno Yang Yachin from the, it's a doctoral researcher, IMD 3, photovoltaic for something. Julius.
Genau.
Okay, thank you.
Thank you very much. It is my pleasure to be here. So I'm Yakin, I'm from the Research Center ULIS. Today I would like to talk about our research on the PCVD of transparent conductive oxide for silicon heterojunction solar cells. So in general, I will talk about the motivation behind the research, the development that we do to have this PCVD TCO of undoped and boron-doped zinc oxide, and I will show you some self results and analysis, and then also the summary and outlook. So if we look at the recent silicon heterojunction solar cell structures, so we started with the N-type crystalline silicon wafers sandwich between the intrinsic amorphous silicon layers, and then on top of that, we usually have either nanocrystalline silicon or nanocrystalline silicon oxide. And on top of that, we have the transparent conductive oxide layers, and finally, we have the cells with the silver contact. So the transparent conductive oxide layers, known as the TCO, act as a lateral transport of the charge carrier, and it is also act as an anti-reflection coating to optimize the incoming sunlight being absorbed in the silicon wafers. So the way the TCO layer being deposited is usually done by a method called the sputtering. So the sputtering, it's basically you have the target materials, let's say indium tin oxide, and then in this sputtering process, you have high energy plasma, which can bombard the target materials, and then you will have an ejected atoms or particles from the target that can go through the chamber and then condense on the substrate, forming the thin film deposition. But it is very well known in the community that the sputtering process can damage your substrate, and this sputtering damage mainly comes from several sources, including the electrons, the plasma radiation, the ion bombardment, and also the some process environment. So we can categorize the sputter damage actually into recoverable and non-recoverable. So in the case of the silicon heterojunction, for example, when we do the sputtering, this process might break the silicon hydrogen bond, but usually we have the annealing and light soaking process, which can basically resolve the issue. But there are also some cases in which when you do the sputtering, you create a permanent defect at the interface. For example, you have the ion implantation, you have the loss of the hydrogens, in which you no longer get you no longer recover the sputtering process. So, for example, in our institute, we did some sputter damage investigations. For example, here we show the effective carrier lifetime with the sputtering at two different conditions, one being recoverable and one being non-recoverable. We also simulated the ions penetrated into the amorphous silicon, crystalline silicon interface, depending on the energy which is typically used in the sputtering process. So, although the most of the sputter damage in the silicon heterojunction solar cells can be recovered, exploring the new damage-free TCO process might be beneficial for many applications. So here we have the sketch of the PCVD. So unlike in the sputtering, in the PCVD, you develop your thin films by having the chemical reactions. So in our case, we develop undoped and boron-doped zinc oxide with these precursors. There are definitely some advantages of using PCVD. So you have the less ion bombardment, for example, and you can also control the thin film depositions. And specifically for silicon heterojunction, this PCVD process might have huge potential. For example, we can further optimize the existing passivating contact, for example, make the film thinner by having the soft deposition technique, or we can allow new ideas, new materials for the film being developed. And it is also more important for tandem applications later on. So yeah. In our group, we try to develop the PCVD process of zinc oxide and boron-doped zinc oxide. Here I will show you the optical and analytical properties of the film. We also applied this TCO on either front side or the rear side in our solar cells. And this is how our solar cell looks like. So it has 4 subcells, which each subcell has area around 4 square centimeter. So, yeah. initially we did some process optimizations to get a good optical and electrical properties of our zinc oxide films. And if we look at the optical properties right here, we can clearly see that the film that we develop is okay. It's promising. It has a good transparency and it has a low absorptance, which is quite comparable to the reference sputter Adzo. And if we compare the undope and boron dope zinc oxide, you can also see the absorption shift in the boron dope zinc oxide due to the larger band gap, which is understandable. But if we look at the electrical properties comparing the undope and boron dope zinc oxide with the boron dope, definitely you have more carrier concentrations. But when you introduce impurities, you have more carrier concentration, which can also act as the scattering center. Therefore, you have a reduced mobility. But overall, with the boron dope zinc oxide, the resistivity drops, which is promising. Yeah, and then if we compare the boron dope zinc oxide to our well-developed sputtering Adzo, there is still a gap in terms of the mobility, which require further investigation and further optimizations. So we are done with the development of thin films. We applied directly to our solar cells. So we either applied on the front side or on the rear side. And here we have the undope and boron dope zinc oxide, and we have also the dashed line corresponds to the sputter reference. Yeah, at the moment, if we look at the VOC and the JSC, there's still a gap between our PECVD TCO to the sputter TCO. We believe that it is because of the relatively poor materials that we have at the moment. And as you can see, for example, in here, we have a very low fill factor, which mainly comes from the series resistance, so which indicates that the TCO that we develop with PECVD is still relatively poor. But this is our first time in using the PECVD TCO directly on silicon heterojunction solar cells. But yeah, and then the question is why the series resistance is so high, even though previously we have shown that the electrical properties is quite acceptable. So apparently, when we do the silicon heterojunction fabrication process, it has the curing step, which is the annealing in air after we screen printing the silver metal. So definitely, because this additional annealing step, it changes the electrical properties of the film. So in the case of the TCO, usually we have the oxygen vacancy, which contribute to the charge carrier. And then when we do annealing in oxygen-rich environment, yeah, these oxygen species can be absorbed on the surface or on the bulk, which can replace our oxygen vacancies, for example. And this can reduce the carrier concentration of our film. Also, these oxygen species in the films can also trap the electrons, which limits the mobility of our film, like shown in here, and yeah, which result in the film resistivity increasing 1 to 2 order of magnitude, which is not great. There are several ways how we can mitigate the issue. For example, we can utilize to add a cupping layer to protect the PECVD TCO that we have, or we could also process with some extra treatment. So what we did, we have the hydrogen plasma treatment right after annealing. So, and here we show the improvement of which eventually improved the solar cells, especially the fill factor in here. So what happens actually with the hydrogen plasma treatment? So with the hydrogen plasma treatment, you can neutralize or you can dissolve the oxygen species. You can also weakly bond the oxygen species. So then you have the carrier concentration back. The hydrogen plasma treatment can also act as a shallow donor. So you also have the free charge carrier. And yeah, with the hydrogen plasma treatment, it is also known to pacify the defect in the materials, which can improve the mobility. So as you can see, after the hydrogen plasma treatment, we improve the current concentration back, and also we improve our mobility back. So in this case, the resistivity of our film goes down again, which you can see in the solar cells result. We have a huge improvement in the fill factor and also drop in the series resistance, which results the efficiency of our solar cell around 16.4%. So I think that's pretty much the talk of about our PCVD TCO. So basically, we have the sputter damage, and we can utilize the PCVD as a new route to develop the TCO layers, especially in heterojunction solar cells. And yeah, this is our first report to utilize this in solar cells and showing some efficiency around 16.4%. Definitely, there are more work needs to be done. So yeah, we need to vary some dopants or how we can maintain the electrical properties of the film. So yeah, I think thank you very much for your attention. I would like to thank my colleagues from Research Center Jülich. Thank you.
Turn it on? Yeah.
Yes.
I'm Jitendra Sehgal, President R&D from Borosil, India.
Yeah.
I want to ask you one thing. Can you go to slide number 11? The second last slide.
No, I can't.
You cannot? Okay.
I cannot.
Okay, let me go and ask the question directly then. So you said you did the hydrogen plasma treatment,
yes.
right? And you said, so did you also measure the OH concentration in the film after hydrogen plasma treatment?
At the moment, we haven't measured the hydrogen or OH concentrations characterizations. So we just measure the film before and after this hydrogen plasma treatment, and also the solar cells before and after plasma treatments. But definitely, it's going to be in that direction that we understand what is really going on with the hydrogen plasma treatment, how it affects the hydrogen content, for example, in our film.
Yes,
yeah.
Actually, to understand the mechanism, it's very important, yeah?
Yeah, thank you.
Any other question? Okay, no question. Thank you.
Thank you.
So it's the last topic of this session. So right now it's 3:30. We still have a rest about 45 minutes. Okay. Half an hour. Okay. 4 o'clock. Come back. Okay. Okay. Thank you.